All right, let's get right into it. Today, we are breaking down a really fascinating high-stakes intelligence mission called Operation Snake's Nest. We're going to crack open the logic behind this thing and see how a really clever, kind of unconventional search strategy can totally conquer a massive digital battlefield.
So, let's just start with the core problem here. How do you find one single hidden target when there are over 30,000 possibilities? I mean, a normal brute force search would be way too slow, and worse, it would set off every alarm they have. So how do you find that one critical weakness in this enormous digital fortress without, telling the whole world you're there?
So the mission itself was codenamed Operation Snake's Nest. And here's the basic briefing. Okay, so the objective, it sounds pretty simple on the surface, right? Just find one enemy server, the Snake's Nest. But this isn't just any server. This thing is the command center. It's the absolute heart of their entire network. And it's tucked away somewhere inside this massive, hostile digital wilderness. Now, before you can plan any kind of attack, you have to understand the terrain. So the very first step is to map out this digital battlefield. The entire search area, it's officially known as the Mega Matrix. Just think of it like a giant digital map, a grid where every single little cell is a potential hiding spot for a target. And the scale we're talking about here is it's immense. This isn't some small search area. This grid is 176 cells wide by 176 cells high. And if you do the math on that, you really start to see the true size of the problem. It comes out to a staggering 30,976 individual cells. Just let that sink in for a second. If you scanned just one cell per second, it would take you more than 8.5 hours to get through it all. And the whole time, the enemy is watching. So a brute force search isn't just slow, it's basically mission suicide. And this is the crucial piece of intelligence, the one detail that changes everything. This field isn't just a random mess of cells. It actually has a hidden underlying structure. And here it is. This is the game-changing detail. Technical analysis showed that this huge mega matrix wasn't random at all. It's actually a grid of smaller 8x8 grids. So the battlefield isn't one giant featureless map. It's a giant board made up of, well, chessboards. And suddenly, our whole problem transforms. Instead of searching one massive featureless desert of 30,000 plus cells, we're now navigating a structured city of 484 distinct neighborhoods, or chessboards. Knowing that structure, knowing where the boundaries are, that changes the entire game. And all of that brings us to the solution. To navigate this complex structure, the operators came up with a pretty unconventional approach, the diagonal search strategy. A standard search, going row by row, line by line, is slow, it's predictable, and it immediately sets off enemy defenses. The diagonal search, on the other hand, is fast and totally unconventional. It's specifically designed to evade detection. See, most security programs are built to spot obvious patterns, like a scan going row by row. This diagonal path, to them, it just looks like random noise. The official name for this strategy is the triangulation search. And the reason is that as the search moves forward, the area it's covered forms this expanding triangle. It starts in one corner and just sweeps across the entire grid in these diagonal waves. Okay, so let's trace the first few steps so you can see it. The search kicks off in the absolute bottom left corner. The next step isn't just moving right or up. Instead, it checks the 2 cells on the next diagonal line. The step after that checks the 3 cells on the next one. You can see the pattern, right? It's like this expanding wave, sweeping across the grid one diagonal slice at a time. So we have the map and we have the strategy. Let's deploy the scanner drone and actually see this search in action. The drone starts at its global coordinate, 175,0, and by doing some quick math, basically just dividing its coordinates by 8, it knows its precise local address. It knows it's on chessboard 21,0, which is the very last board in that first column. So the drone gets to work scanning cell after cell, following its diagonal path. Now, let's jump forward in time. After a whole bunch of iterations, the drone arrives at the global coordinate 179.
Now watch this. As the drone analyzes its position at 179, it calculates that it is now on chessboard 21-1. Without ever breaking its diagonal stride, it has just seamlessly crossed an invisible boundary. It's now operating in a completely new sector.
And this is what so brilliantly shows the power of the algorithm. The search path is defined on that big macro mega matrix level, but it is totally aware of the micro chessboard structure. This lets it systematically breach new sectors without ever having to change its core logic. It's just elegant.
So, what exactly made this strategy so effective? Let's decode the algorithm's power and pull out the key principles that made it work. So, what's the magic formula here? It's really these four ideas working together perfectly. First, you refuse to see the problem as one giant, impossible wall. Instead, you break it down into smaller, manageable blocks. Then you get creative. You choose the unexpected path, the one the enemy's defenses just aren't built to detect. But, cleverness is nothing without discipline, so the search has to be perfectly systematic, making sure nothing gets missed. And the final, really elegant piece is this ability to operate on two levels at once, following the big, sweeping path across the whole map, while always knowing your precise location within each tiny neighborhood. This quote from the mission analysis just sums it up perfectly. The genius here is in the two-level thinking. You have a single, elegant path that operates on the macro level, while it's constantly aware of its precise location on the micro level.
And that really brings us to the final takeaway. I mean, this was about more than just finding a server. It was about reframing a problem. So it kind of leaves us with the question, right? What complex problems in your world, big or small, could you solve just by changing your angle of attack?